This is the second video in a mini-series of videos that I'm making, giving an introduction to a treatise on conic sections by Apollonius of Perga. In the first video that I made, I went through some of the historical background, some remarks on the different translations of the work that are available, and I introduced some basic notions, definitions and terminology. But in this video I intend to really make a start on the main body of the work. So Apollonius kicks off his treatise with a classification of the different conic sections. So that's where we're going to start now. I'm going to go into quite a bit of detail with this because some of the ideas that are involved are quite fundamental and are used throughout the rest of the work. So I'm going to go into quite some depth with this. Having said that, I don't intend this video nor any of the other videos that I make to be a fully comprehensive treatment of Apollonius's work. It's really just giving an overview, but some of these notions in this first part of the work really do deserve quite a bit of time to be spent on them. So let's get started. So let me just explain this diagram to you. Here's our cone with the base circle here. BC is the base circle, and the centre of that base circle is O. So therefore AO is the axis of the cone. So in the previous video I talked about the axis of a cone, and what I've done here is I've taken a slice through the cone with a plane that is parallel to that base. Okay, so that's this thing here. It produces a section of the cone. Strictly speaking, there are different cases that I could consider here, namely whether the section that I take is between the apex and the base, whether it's below the base or whether it's even on the second. Remember, this is really a double cone. If I were to extend up there, I could cut through there, but the argument that I'm going to use in a second is applicable to all three exactly as it is. And okay, so what I'm going to do is I'm going to take a point P on the circumference of that base circle. So it could be any point, so let's just say for sake of argument that it's here. And now let's turn our attention to this thing here. Well, this axis that goes through A and O is also going to intersect this section at some point, so let's call it O primed. And I'm also going to draw a line straight from A to P. So this is one of the generators of the cone, and therefore it must intersect the section at some point P primed. Okay, and I'm going to join the points O primed to P primed, just as I've done in the diagram. So therefore the lines A, O primed O, that's a straight line. A, P primed P is also a straight line, and obviously OP and O primed P primed are straight lines as well. Not only that, because this plane is parallel to the base, then any line in the plane is also going to be parallel to any line in this plane. So therefore O primed P primed is parallel to OP. The upshot is that triangle A, O primed, P primed is similar to triangle A, O, P. So I'm just going to use this symbol for now to indicate that the triangles are similar. So if we've got similar triangles, then their sides are going to be, their corresponding sides are going to be proportional. So from that I can say that A, O primed, the ratio of A, O primed to AO is going to be equal to the ratio of O primed P primed to OP. Okay, so this is this ratio is derived purely from the similarity of the two triangles involved. Okay, well, the axis of this cone it's a fixed thing. Okay, I can extend it, but it doesn't change its position in any way. Similarly, the base circle doesn't change. So that means that the distance AO is a fixed distance. It doesn't change. What can change is the position of P, but wherever P is, doesn't matter. It doesn't change the anything to do with the axis of the cone. Similarly, the intersection of the axis with this section doesn't change because the axis of the cone doesn't change, and nor does this plane. So therefore, this side of the this ratio is a constant. Okay, it's a constant value. Also, with this being a circle, the base by definition is a circle. It doesn't matter where P is on the circumference of that circle. It will always be a fixed distance. It will always be the same distance from O. That's the definition of a circle. A circle is the locus of all of the points that are a fixed distance from a specific point, in this case O. So OP is also constant. So what this means is that this can't vary. The distance can't vary. Even though the position of P prime can vary, the distance between O prime and P prime can't vary. Because if it did, let's say that it increased for some particular value of P prime, that this was bigger, then this ratio would be bigger. But this ratio would have stayed the same, so we wouldn't have equality there. So the only solution to this is that the distance O prime P prime is actually the same, irrespective of the position of P prime. So O prime P prime is a fixed distance. So what that means is that the section that's being cut here must be a circle. Again, the definition of a circle is the locus of all of the points that are a fixed distance from a specific point, that specific point being O prime in this case. So what we get from this is that if we cut through a section parallel to the base circle, what we'll get is a section that is another circle. Just before I move on to the next bit of Apollonius's work, I just need to quickly introduce a notion, which is that of a subcontrary, or cutting on a subcontrary angle. So let's say we've got a triangle. Such as this one. Then there are different ways that I can cut through this triangle to get other similar triangles. So one of the most obvious ways is for me to cut with any line, for example, parallel to this side. So let's say I cut with that line. This is parallel to this side, so therefore this triangle, the smaller triangle, is going to be similar to the larger triangle. But that's not the only angle that I can, type of line or series of lines that I can cut with to get similar triangles. I can also cut in what's called a subcontrary sense. So if I cut in such a way that, let's say I cut with this line, such that this angle here is actually the same as this angle here, then I've cut in what's called a subcontrary sense. So obviously this angle up here is common to both of the triangles. If these two angles are equal, then these two angles must also be equal. So therefore this triangle here must be similar to the largest triangle from which it's being cut. So this is going to play an important role in the next little bit of the video that I'm going to be going through. So let me just explain this diagram that's behind me on the board. This is our cone, axial triangle ABC. The base of the cone is here, so the circular base of the cone, that is. And we're going to choose a point on the circumference of that base circle F, and through F we draw a line to the base of the axial triangle, meeting the base of the axial triangle in L, such that FL is perpendicular to the base of that axial triangle. And next, for the time being as well, if we just assume that the axial triangle is actually perpendicular to the base, it'll just make things a little bit easier for us to deal with. Next, I'm going to take a slice through the cone with a plane in a subcontrary sense. So that's going to produce a section the diameter of that section is going to be hk. So diameter in the sense of how I introduced diameter in the previous video. But because it's cut in a subcontrary sense, then that means that angle AKH is equal to angle ABC. Okay, and from any point, I'm going to choose any point on that section P, and I'm going to draw a line through P to HK, so meeting HK and M such that PM is parallel to FL. In fact, the only purpose, the only function of this line FL in what I'm about to do is actually to give me the right positioning for this PM. And I can produce that if I want to the other side of the section to P prime if I want to. I don't actually need to, but you can do that if you want to. So wherever PM meets HK, through that point M now, we're going to cut another section, so that's this red plane here, parallel to that base circle. So as we've seen from previously in this video, that is going to be a circle. If I cut through parallel to the base, then that's going to give a circle. So this red thing here is actually a circle. And PM P primed is going to be a chord in that circle, and so is DME. That's also going to be a chord in this circle. So now let's just turn our attention to these triangles HMD and EMK, which are formed by the intersection of DME with HMK. So clearly this angle here is going to be equal to this angle here, but also because I cut through in a subcontrary sense, then also AKH, this angle, is equal to the angle ADE. So I know that angle ADE is the same as angle ABC because I cut parallel to that base circle. So any angle that's equal to ABC must also be equal to AKH. So that means that triangle DMH is similar to triangle MEK. So I can use that similarity now to derive some ratios between the sides of these similar triangles. In particular, the ratio HM to MD is equal to the ratio ME to MK. Okay, and then I can rearrange this ratio to get that HM times MK is equal to ME times MD. So where does this come from? Well, if you watch the previous video, the first part of this series of videos, right at the end of the video I went through some of the results from Euclid that are particularly useful when it comes to Apollonius, and this is one of them. Okay, so if you want a bit more information about that, worth looking back at that video. So we know that the red section here is a circle. So with it being a circle, it must satisfy the intersecting chords theorem. The intersecting chords theorem must be valid. So therefore, the two chords that we're interested in are DME and PMP primed. So that means that ME times MD must be equal to PM times P primed M. But these are equal in length because remember, HK is a diameter in the sense that I introduced in the first video, so therefore M must be the point of bisection of PP primed. So this is equal to PM squared. So that means then that not only do we have that the intersecting chords theorem is valid in this red circle, it also seems to be valid in this black section that I cut, because we've got that hm times mk is equal to pm squared. Well, that is the statement of the intersecting chords theorem. So that means, because p was an arbitrary point on that section, then this is valid for all such chords within that section. So what that means is that the section that I've cut, this black section with diameter hk, is actually a circle. So that means that if I cut a cone through on a subcontrary angle, then I get another circle. So contrast this with maybe how if you were to cut a right cone, for example, if you had a right cone, an isosceles cone, you can only cut parallel to the base to get a circle. Cut on any other angle, you're going to get a different type of section. But when you've got an oblique cone, which is what we deal with generally in Apollonius's work, then we can cut parallel to the base to get a circle, but we can also cut on this subcontrary angle as well to get circles. So it turns out that these are the only two angles that we can cut on to get circles. Apollonius goes on to show that cutting on any angle other than parallel to the base and on a subcontrary will give something that is not a circle. So he's not more specific about it straight away, what kind of sections we're going to get. He just says that anything on any other angle other than these two is going to be a section that is not a circle. Then he continues his classification by showing that if you cut at some angles, certain angles, you'll get finite sections, and if you cut at other angles, you'll get infinite sections. And presumably there are no sections that can be considered both finite and infinite. So this would give a kind of partitioning of the different types of sections. Now we can see that circles are obviously going to be a type of finite section. So when I say finite, think of them almost as being contained in a small region, or a small enough region of space, whereas an infinite section, no matter what region of space, it's always going to kind of break out of that region of space. So presumably there are no sections that could be considered as both finite and infinite, or neither finite nor infinite. So circles are definitely one of those types of finite section. There's at least one other type of finite section, and then we've also got these infinite sections, which as yet we don't know anything about. So this is starting the more kind of detailed, the finer classification of the different types of section. So the rest of the next part of the video, I'm going to be continuing with that classification. Okay, so this is the next diagram that we're going to be working with. Just let me explain what's going on here. Now, the diagram, it does look quite cluttered. There does seem to be a lot of information in there, but this is just the nature of what we're dealing with now. There's a lot of information, but it is all necessary. So as usual, we've got our cone, axial triangle ABC, and what we're going to do is we're going to cut through the cone with a plane, such that the plane of the section and the plane of the base circle intersect in a line DME, which is perpendicular to the base of that axial triangle. We're also going to cut in such a way that this line PM is parallel to AC. Now, if you remember from if you've watched my first video, you will know then that PM in this way is going to be a diameter of the section that we've just cut. So the section that we've just cut is this blue bit here. Then we're going to take any point on that section, Q, and we're going to join it ordinate wise to the diameter PM. So it's going to we're going to draw a line QV. Q is on the section, V is on the diameter, and the line QV is drawn ordinate wise. So again, from the first video, we know that QV is actually going to be parallel to this line DME, with it being drawn ordinate wise. And next we're going to cut through with another plane, a plane that contains that line QV, and which is also parallel to that base circle. So that's this green thing here. So that is itself as well going to be a circle, as we've seen from earlier in this video. Cutting parallel to the base is going to be a circle. So QV and HVK are contained in that plane, in the plane of that circle. And finally, we've got this thing sticking out here. So this is a line of a particular length, which I'll talk about in a second. But we imagine this drawn in the plane of the section. So PL is drawn in the plane of the section, but perpendicular to the diameter. So that doesn't mean that it's necessarily going to be parallel to QV or anything like that. Maybe it might not be, but it's going to, we imagine it perpendicular to the diameter PM, and PL is determined in such a way that the ratio of PL to PA is equal to the square on the base of the axial triangle to the rectangle contained by the other two sides of the axial triangle. So PL is a determined value because these are all fixed values. The axial triangle doesn't change, and if we know where we're cutting through the cone, we know the distance AP, then that means that PL is going to be uniquely determined by this ratio here. Okay, so in particular, because this green section here is a circle, then the intersecting chords theorem is applicable in the following way. So we've got V times VK is equal to QV squared. So this is, if I were to extend this line, then I'd get an intersection down here, maybe Q primed. But remember, that's being drawn ordinate wise. So it's parallel to DME, so it's bisected by the diameter, as in the first video. So Q primed V would be equal to QV. So that's where this comes from. And now we've got some similarities between some of the triangles that we can pick up on here. So in particular, we've got triangle PHV is similar to triangle ABC. So due to the similarity, we can derive some ratios regarding the lengths of the sides. Now, which ones do I want? So I want HV, ratio of HV to PV to be equal to HV PV, BC to AC. Okay, and I'm just going to highlight that because that's going to be an important ratio, or an important equality for us to use in a second. And okay, the next one, we've got two similar triangles here in PHV and AHV. So therefore, the ratio of HV to HK, that's probably be better for me to write it the other way around. So HK to HV is equal to AH to HP. And then I can use separando. So I talked about this briefly at the end of the first video that I made. So HK minus HV to HV is equal to AH minus HP to HP, but as you can see, HK minus HV is just VK. 2HV is equal to AH minus HP, which is just AP, to HP. Okay, and then rearranging this, I get that VK, the ratio of VK to AP is equal to HV to HP. But I know that this triangle PHV is similar to ABC. So HV to HP is equal to the ratio of BC to AB. Okay, and this is going to be our next useful ratio. What I can do now is I can effectively multiply these two ratios together to give the following. So HV times VK to PV times AP is equal to BC squared to AB times AC. So just multiplying effectively the corresponding parts of the ratio. And okay, you might notice then that this is the same as what we had up here. So this is the ratio PL to PA. And this is equal to QV squared. So we've got the ratio of QV squared to PV times AP is equal to PL, the ratio of PL to PA. Using another little trick, I can multiply both parts of this ratio by PV. So I end up with QV squared to PV times AP is equal to PL times PV to PA times PV. Well, this is the same as this. So using, I think it's Euclid book 5 proposition 9, I think, I can say that finally QV squared is equal to PL times PV. And this is quite a significant result at this stage, because this gives me another and more useful characterization really of that line PL. So if you look up here, PL, it's determined, but it's given in a very kind of cumbersome, it's certainly not an easy format. It's quite clumsy. Not only that, it's kind of determined by, not by the section itself, not by information that comes from the section itself, but information that's kind of around the section, namely the axial triangle. Well, really I want to be dealing with the sections themselves rather than having to worry about exactly the exact environment from which they've come from. So this allows me to do just that. This really completes the picture between the diameter, the relationship between the diameter and the ordinates, or the abscissa with its ordinates in a given section. And any section that satisfies, that has whose ordinates and abscissa, QV being the ordinate and PV being the abscissa, any section that has this relationship between its ordinates and its abscissa is called a parabola. Okay, so PL really completes the picture. And notice that the word parabola is used to classify a section in terms of really its this PL here. The name of PL is, its Latin name is the latus rectum, or it's sometimes usually referred to as either the parameter to the ordinates or just the parameter. Heath tends to use the word parameter in his work. So a parabola is any section whose abscissa and ordinates are related to one another in such a way with the parameter PL. Sometimes a lowercase p is used instead of PL. But the categorization, the classification of parabola is not based on the appearance of the section, nor is it based directly on how the section has been cut from the cone. Although those will, in a way, come into the picture, it's a much more neat classification, much more objective kind of classification via this. And this mirrors maybe in modern treatments of conic sections, where the type of conic section that we're dealing with is the classification is along the lines of the eccentricities, in terms of the eccentricity. So if you've got something, a section whose eccentricity is greater than 1, and it's a hyperbola, or if it's between 0 and 1, then it's an ellipse, for example. This plays a similar kind of role now. And what I'm going to show in a second is, I'm just going to give a bit of an illustration, a bit of a more visual illustration about how the parameter works for a parabola, but I'm also going to show how it works for the other sections as well. So the diagram here just gives a bit of a visualization, really, for how the parameter and the section to which it's related kind of work together, how they fit together. So this is a parabola in here. So we know from what we've just seen that the ordinates and the abscissa and the parameter PL are all related via this equation here. So a visualization of that is this. If this is a diameter, so I've just drawn the axis just to make it a little bit easier to work with here. We've got the axis here, and QV is an ordinate, so we've got the square on QV. So we're talking about the area, this blue area here, that's QV squared. Well, this has to be equal to the rectangle with sides PL, PV. In other words, the area of the rectangle with sides PL and PV. So if this is the abscissa, PV is the abscissa to Q, then PL has to be such a length to make this red area equal to this blue area. And now, because we've kind of detached the parabola, the section, from all of this surrounding environment, the actual cone and the axial triangle and things like that, we can kind of start to play around with the section and the parameter and vary things to see much more clearly how they work with each other and how they're related to each other. So in particular, if I were to increase PL, the length of PL, what effect would that have on the parabola? Because surely it couldn't be the same parabola, because if I increased PL here, but the others didn't change, then, well, actually I wouldn't have equality. So something must give somewhere. Well, if I increase PL, remember PL is a fixed value for a given parabola, then what that's going to cause is kind of quite a wide parabola. So it might, if I were to increase PL here, it'd make the parabola go maybe more like that, a bit wider. Why is that? Well, the longer PL is, the less PV has to work, in a certain sense, to make sure that this area keeps up with this area here. Remember, these two areas have to be equal for this to be a parabola. So having a longer PL means that PV doesn't have to increase as quickly. Whereas if PL is much shorter, PV's got to race along the diameter, or in this case the axis, much faster to keep up with the growth of the area of this thing here. So what that's going to create is kind of a really narrow parabola that grows very quickly in that direction but very slowly in that direction, whereas conversely longer parameter means that the parabola grows very quickly in this direction. So that's how the parameter works in relation to the parabola. We need to have a look now at how the parameter works in relation to the other possible sections, and this continues the classification. Okay, so we've already looked at a very specific case where we cut through a cone effectively parallel to one of the sides of the axial triangle. But now we're going to consider, we obviously need to consider more general situations where we're cutting through it at various different angles. So what we're going to do is we're now going to imagine cutting through the cone on an angle that's kind of shallow enough to produce a finite section. So as you can see here in the diagram, this is the kind of angle that we're going to be cutting on. So this top bit of the cone here, this double cone, doesn't really come into it. We want to choose a plane that definitely cuts straight through one of the cones. So this is going to be a finite section. We know that circles are an example of finite sections. They come about specifically when we cut parallel to the base circle or if we cut on a subcontrary. But we also know that there's all the angles in between. So we need to consider what happens in those cases. So just like with the parabola, we started out with this PL, what became known as the parameter. We're going to do a similar thing with the new type of section. I'm not actually going to go through this in too much detail because Apollonius goes through it quite well in his work, but it's roughly the same kind of idea, so I don't want to get too repetitive. So with the parabola we defined this PL. The length was determined in terms of its ratio and its relationship to various other lines and magnitudes, particularly relating to the axial triangle. Well, for sections cut off in this way, we can define PL in a similar kind of way, but the ratios are a bit more involved. So this is why I'm not planning on going into too much detail with it at this stage. But from that relationship, it turns out that we don't get, as we did in the case of the parabola, QV squared equals PL times PV. We actually end up with QV squared is equal to PV times VR. Okay, so it's the same kind of idea. It's the area of some square. The square on the ordinate is equal to the abscissa multiplied by, in the case of the parabola, it was the parameter. In this case, it's this thing VR. It's not the parameter. So we're still thinking of PL as the parameter, but this is not it. This is something different. Okay, so how does this come about? Well, let's say that this is the section that we get. And with it being a finite section, we also know that the diameter that results from this is going to have two definite intersection points with the section itself, namely P and P primed. And just to make a point here, the line segment PP primed is called a transverse diameter. So this is going to play an important role further down the line with some of the stuff that I'm going to be going on to in the next video. So this is roughly what our section is going to look like. We take a point Q on our section and we join it ordinate wise to the diameter PP primed. And I've just produced the line a little bit. So this is this blue line here, and this is the square on QV. So this blue region here is the square on QV. Well, as you can see from the relationship here, it's PV times VR. Well, PV is the abscissa. VR is, if I produce QV, it's a certain length, certain distance along that line from V to r, such that the area, this red area here, is going to be equal to the blue area here. So how is this r determined? Well, as you can see from the diagram, if this is the parameter PL, which has been defined through these other ratios, then if I join the endpoint of PL to the opposite end of the diameter, so P primed in this case, then where that line, LP primed, intersects QV produced, that is where R is. Okay, so as you can see, VR is necessarily less than PL, so we could also say that QV squared is less than PV times PL for these sections. And this is basically the characteristic property of sections that are cut at such an angle from the cone, that they satisfy this property, and this is how you can visualize it. So it's kind of a similar concept, so it's matching up areas just like with the parabola, but the areas are a bit more difficult to get to. We've also got, because in reality R could be possibly quite difficult to obtain, we can from this derive a ratio, namely that QV squared, the ratio of QV squared to, let me get this right, PV times P primed V is equal to PL to P primed. Okay, so that gives some relationships involving PL directly with the length of the transverse diameter, and this is the abscissa, and this is kind of the remainder along that transverse diameter, and this is the ordinates. So this gives a nice relationship that doesn't involve this slightly more awkward thing, this VR. So one of the questions that obviously would need to be addressed in reality is how can we guarantee that PV times VR is always going to be equal to QV squared? That's what Apollonius goes to in his work. So, like I said, these are characteristic properties, really, of sections cut at this particular angle, or similar angles. And as such, we can classify these, we can put them all into a single category, and the name that we give to such sections is an ellipse. So now we just need to consider the final ways in which we can cut this this cone now. So we've already considered the cutting parallel to one side of the axial triangle, cutting on a nice shallow angle, so that we cut straight through one of the cones. Well, what about if we cut now with a steeper angle, so steep in fact that we actually end up cutting through both of the cones to a certain extent. Okay, so now this second cone up here is coming into play. So there must be an intersection up here, by the way. So if these two lines, the green one here and this side of the axial triangle, if they're not parallel, then obviously there must be a point of intersection, but it can't be down here because the lines are getting further away, so it must be up there somewhere where they intersect. So just as before, there's two definite points of intersection with the diameter with the section itself. Now I'm concentrating here on just this lower bit. We're not going to get into too much detail right now about what this looks like up here. But if you look at the diagram that I've got here, this P is effectively this point here where we're cutting into the cone here, and P primed is the point of intersection up here. And just as before with what became known as the ellipse, this is called a transverse diameter as well. These are going to be really important when I get onto the next section in the next video, when I start to introduce conjugate diameters and things like that. So this is called a transverse diameter. Well, again, starting out in the same way as we did for the ellipse, we define the parameter PL in a particular way, so it's it has a certain ratio and relationship to other lines and magnitudes, and from that we get a similar kind of relationship between the ordinates and the abscissa, namely qv squared equals pv times vr. Now this looks identical to what we have for the ellipse. So how do we distinguish an ellipse from this type of section here? Or is this still going to be an ellipse? What we're going to get when we cut on this? Well, presumably not, because it's going to be an infinite section. So it can't be an ellipse, because an ellipse is finite, so it must be something different. So what distinguishes this from what we got with the ellipse? Well, the diagram here will kind of illustrate what's going on. So we're still trying to match up the areas, the square on the ordinate with the rectangle contained by the abscissa being one side and another line, this VR. But how is VR determined in this case? Well, in a similar way to the ellipse, but because the transverse diameter is kind of on the outside really of the section. So in the ellipse it was going actually through the ellipse. Here we've got our section, the transverse diameter is kind of on the outside a little bit. So when I draw a line from P primed through L, if I produce that line further, so that it intersects QV produced, then that is my R. Okay, so QV is my line drawn ordinate wise, joining Q to the diameter here. So QV produced will meet P primed L produced in R, and that is this VR here. Okay, and therefore this blue area, this square, is going to be equal to the area contained in this rectangle. So from this we can see then that QV squared is actually going to be, I guess, greater than PV times PL. So that distinguishes it from what we had before, because with the ellipse we had QV squared was less than PV times PL. With the parabola we had QV squared was equal to PV times PL. So this gives a new characteristic property of these particular types of sections. Again, we've got the relationship in terms of ratios, namely QV squared to PV times P primed V is equal to PL to P primed. So that is identical to the relationship that we had for the ellipse, but the thing that distinguishes this from before is effectively this. Again, Apollonius goes through this in quite a bit of detail in his work. Heath's presentation of it is, I've used Heath's notation basically for all of this. So any section that is cut in such a way and that will satisfy these relationships. So there's no doubt about it, that's what's proved in Apollonius, that any section cut in this way will satisfy these. And therefore, again, we can kind of lump all of these together and we'll call them, in this case, a hyperbola. So I'm going to add that now to here, hyperbola. And just as a final remark regarding what's going on up here, going back to Apollonius, Apollonius shows that this is basically another hyperbola. Now we can either consider a hyperbola with just one branch, or we can consider both of them together, both branches together, in which case both hyperbolae are going to be identical, and this point P primed here is going to be kind of the vertex of the other hyperbola over here. And moreover, they'll have the individual branches will have exactly the same parameter in terms of the length of the parameter, which kind of makes sense, but it is all proved in Apollonius's work. So now we've gone through the complete classification of all of the conic sections. There's no other way that we can cut any other sections from here. So there we have it. We've got hyperbole, parabole, and ellipse stroke circle. So that's everything for this video. In the next video, I'm going to move on from the classification, and we're going to start looking at some properties involving diameters and tangents and things like that relating to the conic sections. So we're really going to dig into the theory a little bit deeper. So I want to thank you for watching this video, and if you've got any comments, any questions about anything that you've seen in this video, or anything regarding Apollonius's work, or anything else, then I'll try and answer it to the best of my ability. So thank you for watching, and I'll look forward to seeing you in the next video.